Hi, I'm Shamim Naqvi, CEO and founder of SafeLiShare, and I'm delighted to be present with Randy Bardwell here. Randy, would you take a few minutes and talk about yourself a little bit before we get started on the technical subject matter?
Sure. Yeah. So currently I work in the R&D community at Dassault Systems, specifically in high tech and around data science. But prior to that, I've got over 30 years of experience with companies such as GE and Cerner and Mortara to build and develop embedded systems based diagnostics and clinical research data acquisition devices. So my forte is actually the acquisition of mostly physiological data, but any sort of high bandwidth binary data that kind of exceeds what you would typically see in an industrial IoT situation. So from there, I have some experience with algorithms, clinical predictive algorithms, and these all present some very specific problems that I think we can discuss today.
Very nice to have you and looking forward to our conversation. So I am particularly intrigued that when you and I spoke a few days earlier, you talked about a particular use case that with a wearable device, actually, if I remember correctly, that you discussed with me. Perhaps you could start by by telling us a little bit more about that project that you're working on.
Right. So the project was an embedded systems based generic physiological acquisition sensor. And the concept is it was a very broad-banded, addressable, programmable sensor that you could use for a variety of clinical research data acquisition tasks, be it ECG capture, EMG, EEG, anything that requires analog to digital conversion on the front end. And it also just so happened to be a little bitty tiny web server. So it was addressable. It could receive software updates over the air. And always a part of that was the concept of trust zone security. ARM processors, microprocessors, have a built-in architecture that allows you to have security in silicon. And that's always been my definition of enclave security, is the ability to protect your data from the chip all the way up to the cloud. And you can do that with enclave security and an X.509 certificate methodology of secure transport. However, that data security ends in the cloud. And given that a lot of this data is used for clinical research, you obviously want to share that data. You might want to use it for AI modeling, for ECG algorithms. You might want to use that for clinical research for other multi-parameter studies that you're doing. But the point is once the data receives the cloud on most systems, it's basically just unsecured. And so that's where I really enjoyed the concept and the conversation around, your product and SafeLiShare, and the ability to assign specific, not only security, but addressable characteristics to the data. For instance, if you have a data stream and you don't know if you want to send it to a heart rate variability algorithm, or if you want to send it to an algorithm that does something completely different, you don't have to have an entirely different system. You can basically programmatically send the data to where you want and prevent anyone from not being able to be able to see the data. So that's the thing that I see in conjunction with the BioNet project, as it's called.
So let's tease out some more of the details. You are talking about a device that collects information, and let's say the use case involves ECG data, etc. And so this device collects data at the edge from the patient in this particular case, and you then transmit that information to the cloud to be further processed. Is there some local processing being done at the edge device itself, and what sort of
There is.
processing being done at the edge device?
and it's a point that I wanted to make in that article I posted in LinkedIn. In the data transfer world, there's data transfer for parameter data, say heart rate, SpO2, oxygen perfusion, anything that's small data. But then there's also the need to send, for instance, DICOM images, ECG snippets that have been acquired at 500 samples per second times 12 leads. These are typically large binary objects that typical daily security just doesn't work well with. And so in the Pixie project, the concept was to build a new secure, extensible data transfer protocol that would allow you to better send that data to the cloud. For instance, currently today, the state of the art for GE and Philips to send high-speed digital interface data to the cloud for their command center product is using what they call HSDI. It's basically an XML product. It's a Q2-second XML bolus that gets sent to the cloud. Obviously, you have to de-identify and do all sorts of things to this bolus of data, which should have been a binary stream to begin with. Let's face it,
and you do this data de-identification or data anonymization at the device level.
That's correct. And so
and the goal is to depersonalize the data at
right. My favorite word is to objectify. You're really anonymizing it, but it allows you to treat, for instance, a snippet of ECG data just as a cup of ECG data. It doesn't necessarily belong to John Doe or whatever, but you can include in the meta tag information all of the search parameters that you want for that piece of ECG data. But it allows you to treat the data as data, and therefore all of the things that you could traditionally do with a library. So as well as teaching AI models, you can also use it to pull up. And again, if you were putting together, for instance, a clinical research study on a cardiac output wearable device, you would naturally want to include hemodynamic data as part of that clinical research. This gives you the ability to treat it just as data, not necessarily as John Doe's cath lab from January 1st, et cetera.
And you mentioned the ARM trust zone. So that's a secure enclave on the device itself. And we understand that this allows you to trust the data that is being collected and the processing at the edge device itself can be done inside the secure enclave. What is the issue of this ARM trust zone? What is the problem that you solve by having this trust zone?
Well, typically trust zones are used almost exclusively for TEE, or trusted execution environment. And so the use of capturing a certificate to include in what they call an X.509, which is a secure transport layer of data. So you're basically adding a little certificate to that data transfer layer. So anytime you intercept that data protocol and open it up, you would know exactly where it was coming from, and it would be encrypted based upon trust zone. So ARM microprocessors, which comprise, probably half of the market, have had that ability for some time, but nobody was really using it in this data transfer certificate format until the Pixie project.
So you not only have the notion that the edge processing was secure and trusted, but you also have the transport as being secure and trusted.
That's correct. And it's all secure until you get up to the cloud parsing, the Kinesis streaming in the cloud. And then all of a sudden you've taken this stream, you've parsed it out into a SQL or SQL-less environment. And then the data is available without having a protocol encoding set up. So,
and do you envision a real-time transfer or near real-time transfer?
Near real time. Currently, an HSDI file transfer is a 10-second has a 10-second lag, and I think we can do a lot better with that. But it gives you the ability to send snippets of large binary data. So these could be audio snippets. Again, they could be DICOM image files. They could be whole 12 lead ECGs. And it gives you the ability to have an impenetrable force, if you will. The other thing I mentioned in my article, by the way, is if you ask most people about secure enclaves, they'll mention Apple, because Apple, that is the very root of their OS X, is instead of enclave security, they call it secure enclave, but it's a very big part of OS X.
So now you've transferred the data to just to follow the chain of events. You've collected the data at the edge. You have de-identified the data at the edge in a trust zone environment, and you've attached a certificate to say that this processing was done in a secure enclave, and now you have you have this transfer protocol, binary transfer protocol, that is bringing it to the cloud. And in near real time, you want to process this now, and you want to do some predictive analytics or run a machine learning model, etc., and take the results. Why do you care to use a secure enclave in the cloud to do this processing? What is the problem that you're solving at that point?
Well, and just to back up a bit, having the secure enclave data transfer allows you to do things such as, instead of de-identifying, but just indexing all of the PHI, the protective healthcare information, and then providing a binary pointer to it. So it's not like you're taking the data away or having to strip it like you would an HSDI file. So then you do transfer the data to the cloud. The cloud, because of the protocol security, has had what we call 100% chain of custody from the device, basically from the acquisition of the device. And again, it might not be a physiological model. It might be something that's capturing images from a spacecraft. So it gets to the cloud, and then the cloud makes note of it to note in the chain of security where it's at. If it's an ECG model, you would probably want to first cache that in a SQL-less Hadoop environment so that you could recall those snippets, and then you could use a variety of tools. For instance, if you were looking at the clinical problem of long QRS or QRS prolongation, typically the data chain would include analyzing that stream of ECG, and you're looking for heart rate variability. You're looking to parse out the R waves and to count the intervals in between. And so with heart rate variability, then you can do things like with an algorithm from Kubios.com, you can depict that heart rate variability, and there's a number of known algorithms, for instance, for converting heart rate variability into incidence of atrial fibrillation. That's how an Apple Watch works. And so once you get it to that point, you're going to store the data, and you're going to feed that to whatever algorithm you have. And you may have an algorithm such as Kubios for heart rate variability. You might have another homemade algorithm that's for gait analysis. For instance, this device has a 6-axis inertial motion unit, so it can tell if somebody's standing up or laying down. So you might have an algorithm for that. Based upon the protocol itself, you can actually steer it to a different algorithm. And by using data science tools such as model-based systems engineering, you can encapsulate that entire incidence of algorithm, including the definition of the data source, the definition of the algorithm, and the definition of the visualization object, all in one MBSE file. And with SafeLiShare, then you have the ability of not having to build an entirely new clinical predictive analytics server infrastructure. You can simply just send it to a different protocol, and that protocol, MBSE or sysxml file, will be able to define what's going to be the interaction with this data. Is it going to be used for a clinical study? Do I need to allow residents the ability to check out, say, a bunch of hemodynamic files that are based upon particular search parameters. And if I do that, I want to have 100% loggable security over all of those data snippets. And as I see, enclave security is the only solution for that.
Right. So you process these DICOM images or whatever the payload happens to be, and you can, for instance, use the SafeLiShare secure enclave model to do that processing. You have logged security certificates. You have an audit log that is where the processing happened. You re-encrypt this information and you transmit it back to the device, and the edge device can then now transmit that information to the patient or display back to the patient. So that's why I think you call this the edge-to-edge encryption model.
That's exactly right. And again, in the PHI, or the protected healthcare environment, the healthcare environment has a number of added security things that you've got to adhere to satisfy not only HIPAA security, but also GXP cloud certification. And that includes the ability of knowing who, what, when, and where interfaced with your data. And so this gives you, again, a 100% data to cloud and data security, data chain security. Yeah, and data chain of custody is becoming very important in the new focus of clinical AI, which is pathology, especially with slides. And to your point, what confidence do you have that who looked at this data? So there's yet another instance in healthcare, which is the concept of data is confirmed or unconfirmed, as they call it. And in the healthcare data world, an ECG or an X-ray, there's the concept of unconfirmed data. In an X-ray, it's called a wet read, which is the first data that if you're an ER physician, first EKG with the machine interpretation, that's probably okay. But ultimately, that 12-lead ECG or that X-ray is sent to a radiologist or cardiologist who has to confirm it. But how do you know, for instance, who that confirming physician was? In long QRS prolongation, you have two cardiologists that do a blind overread of that data, and you don't have anything other than behind the scenes in the ECG management system to tell you who interacted with that data. And again, for an ECG, it may not be a big deal. People talk about data security between pacemakers and control devices, telemetry devices. That's one thing, but people seem to feel a little bit more lax about who sees this data. And this enclave security gives you the ability to have the most effective methodology of protecting that data.
Have you considered the social aspects of these devices as people walking around and receiving notifications? And maybe you could share a little bit of your experience.
Yeah, it's a great question, because in addition to being a product developer, I also just so happen to be a cardiac patient. And so I've worked in the cardiac industry since Holter recordings were made on reel-to-reels. That kind of dates me. But having worked with technology for the last 30 years, you see that it's gotten to the point where that sort of AI capability is now giving consumer level capabilities. For instance, that 12-lead ECG, when I first started as a Marquette systems engineer in 1982, the ECGs were transmitted via analog, 3 discrete tones that were then received and demodulated and then decoded and then sent to a DEC 1123 mainframe computer. So over the last 30 years, not only have the devices gotten smaller and smaller, but because of the generative effects of AI and learning upon learning upon learning, now the consumer capabilities, and the great version of that is heart rate variability. 30 years ago, you could only find heart rate variability on an ambulatory ECG monitor, a so-called Holter monitor. But now that's basically what runs the Apple Watch. Heart rate variability is then converted into incidence of atrial fib. Some consider that a specious algorithm, but there's different versions of it. To your point, there's probably 20 different versions of that. Just are there many different versions of QTC correction factors. And so being able to see exactly how that data was interacted with, especially as we start adding.
And which version of the algorithm was used.
And which version of the algorithm, right?
There is a cryptographic proof that only that particular version of that particular algorithm was used. Is the key process that sort of assurance can be done by the trusted execution environment.
Exactly. And people may not think much of it now, but I remember an anecdote. So when I worked for the company that invented and self-interpreted EKG machines, I took my wife to the emergency room about 2 years after that, and they had one of our Marquette EKG machines, and they said, "See, it says normal EKG. Even the machine says it was a normal EKG." And we've all just gotten to the point where we just accept that, but nobody really knows the product managers know what the sensitivity and specificity of each of those algorithms are. And dare we know it could become a legal, point at some point. The EKG machine said you were fine, so we based our treatment on that. So yeah, there's a lot of interesting anecdotes that you can piece together for data security.
Right. I'm sure that this is going to cause a lot of social strife, etc., because as these notifications come down to the patients from the result of certain algorithmic processing happening in the cloud. If you receive a notification, it might be an annoyance factor at certain times, or if you don't receive a notification, it may be that you really should have received a notification and you didn't receive it, and that could lead to legal problems and legal issues, etc., which will have to be worked out.
Right. And as a cardiac patient, you look for things that are better than, the previous product. And Pixie originally was designed to be a multivariate device. In other words, it would send ECG, EMG, EEG, but it would also be able to collect peripheral data from glucose monitors via Bluetooth, as well as blood pressures, weight scales, things of that nature. So in the database world, that concept is graph databasing, where you're taking in data from lots of places. And so again, by having some sort of way to manage these data protocols, you can better manage the overall data architecture.
I should mention that the use case that we are talking about in terms of this edge-to-edge computation being secure and private is not just for the world of healthcare and clinical AI, etc., but also we are seeing use cases in other domains. So for instance, we are working with a company, meaning at SafeLiShare, we are working with a company that is into mobile telematics. And these are apps that are carried on the phones of the drivers. And data is collected from the driving and from the situation and the driving characteristics and the parameters from these cars. And notions of distracted driving, etc., are then computed in the cloud. So there are all kinds of use cases that fall into this genre so it's not just healthcare, but mobile telematics is a use case in point.
Right. For instance, I had worked on a data monitoring project that took samples of ECG sounds. And so again, it's not an ECG waveform per se, but even worse, it's a wave file. It has a lot of binary data. And so these are things that you can't encapsulate in the typical MQTT or IoT protocols that exist today. And so as we were working on building a new data protocol, it just made sense to weave into that on the front end the concept of enclave security to the cloud. And then when we discovered SafeLiShare, it's like, oh, well, that addresses the second use case problem, which is how do you share this data? And for instance, if it's a teaching environment where you've got 1,000 physicians and they would all like to have access to data, it certainly solves a number of those problems as well by being able to treat, again, objectifying each of those pieces of data and being able to have 100% chain of security.
Yeah. We at SafeLiShare are very excited about all the different use cases in which edge devices collect and send information that can be processed in secure enclaves in the cloud, and the results of the processing can then be verified and certified. So, Randy, when you have the data coming from the edge device into the cloud, let's talk a little bit about the processing and the regulatory compliance of the data. One of the concerns that listeners may have is that you are going to collect a lot of data from a number of devices, and all this data is going to be in some form aggregated at the cloud level. Now, I know you mentioned that there is data is de-identified at the edge device, and therefore that mitigates some of that risk. But there are issues of data locality, etc., that come into play. Perhaps we could speak a little bit about that from your experience.
Yeah, for instance, we had a large installation company I used to work for in Bern, Switzerland, and in Switzerland, you cannot have a cloud connection back to the United States. Just you can't go outside of the walls of the country. And there's a number of international scenarios that are like that, where you have to have chain of custody over the data to make sure that it's obviously secure, whether it's for territorial boundaries or for security purviews. Again, not knowing exactly what type of data this may be, but especially when you get into graphing databases, products like Neo4j, where you have multiple disparate clouds and you might be pulling data from a genetic database from one cloud and to a electronic medical record system via an Epic hospital information system in another cloud. And you might have the ability to disparately aggregate these data sources to bring them all together for the algorithm. The algorithm knows that the data wasn't de-identified, but the ID was hashed and had pointers such that all of the data was still there in the packet. It was just disassembled and placed in a secure location that you can only disassemble by having the object code that was found in the TEE. So that's one application where you might have data in a number of different places. But in the clinical research world, the actual use case is not only to be able to feed the data into an algorithm, because that's a whole separate use case actually, but it's to be able to look at a number of patients. For instance, if this is a QRS prolongation study, you're going to do a number of 12 lead EKGs on a number of patients. They're all de-identified. This data is going to be brought back and again de-identified, looked at by two separate cardiologists that are going to look at the ECG and denote certain fiducial marks. And so only by having this sort of packet level security do you have 100% control over that clinical research data.
Yeah, but you could also, of course, avoid doing a lot of data, having to do a lot of data aggregation by using techniques that are now being used in federated machine learning models, etc. So, for example, you could send versions of the algorithm to where the data is, and have the results of the local processing of those data sets come back. So you don't aggregate the data, you actually aggregate the results of the local computations being done. So data never moves, but the compute goes to the data in some ways.
Yeah, and it's a good point. There's a lot of interest in data aggregation platforms, companies such as Logic.io, and in the healthcare world, Decisio Health, where basically they're taking a data feed, an HL7 feed in the case of Decisio, and they're providing a para display of real-time data that's quicker to access than going into the Epic MyChart, for instance, and pulling that data out. And so that's one way. It's similar to in an automobile, you've got the CAN bus. That's basically a two-wire topology that sends data every time you hit your button. You're not actually making a contact, you're sending a data packet to a computer that's then deciphering it. So we now live in the world of 100% data. And I think this will be the first, SimpliSafe will be the first way of assigning absolute security to all of those data packets.
Yes, and you essentially share not the data, but you share the versions of the algorithm that does the processing of the data with subject to the rules of data locality.
Right. And in my perfect world, that would and could be done using model-based systems engineering, MBSE technology, because in a data algorithm, you need to know the data stream source, what type of data. You need to know where is the algorithm that we're going to send this to? What do we need to do? Do we need to store it in Hadoop? And then are we going to export this via an HL7 interface? And then what does the visualization object look like? Is it a scatter plot? Is it, something three-dimensional using the Unity engine? All of these are things that are next generation data items that all require the precursor of data security. Right. And there's another data type that we haven't mentioned a lot, but especially in DICOM, where there really isn't a sufficient notion of a watermark. It's one thing for the shareability of the data, but once we're applying AI image detection, which image detection is one of the most useful forms of AI in clinical healthcare. We need to know exactly what version of algorithm that we're using to transform this DICOM image to. And again, that's a good example of a large binary image that's something that you couldn't fit into a normal IoT packet, nor would you want to, because that's why they have the DICOM conformance statement. But the point is in and of itself, it really has no security whatsoever. And as you said, it's not so much just the security, but the chain of custody, who looked at it, who overread it, what algorithm did what was the outcome of that, because there will be a time when these algorithms are so prevalent that you'll really need to keep up with them, I think. So.
Yes, the notions of remote attestation and measurement of algorithms, etc., the code that is actually running in the secure enclave are going to assume more and more importance as this notion of bring compute to data comes in.
I agree.
Comes to the fore. So thank you very much, Randy.
My pleasure.
Look forward to continuing to work with you, and it's a very, very interesting use case. Thank you.
Thank you.